Welcome back, everyone. So today is the third lecture. With your lecture, Professor Guido, and his continuous talk on Equivariant Cohomology.
Thank you very much. So today will be the hour of the algebraic geometer, not so much of the analysts anymore. Today I want to explain somehow the approach Johannes Sprang and myself developed to treat the general totally complex field, which was open before our work. And this will somehow be an analog of what I tried to explain on Tuesday. But today I hope to be more complete, say more, but will require, as I said, some algebraic geometry. So let me first, so the main gadget here are the so-called Eisenstein-Kronecker classes. And I will also point out why we have chosen this name. I need to set up a little bit the stage here. So let's consider a number field L of degree 2D over Q, over the rationals, and it should contain a CM field. So this is, as I said, this is a totally imaginary quadratic extension of a totally real field. And we also fix an algebraic closure of Q in the complex numbers. And we denote by GL the set of embeddings of that field L into Q bar. Yeah, so over Q. So there are in total, there are 2D embeddings. 2D embeddings. And for this theory, it's quite important that you label them in a good way. And for this, you need the notion of a CM type. So we call a subset sigma 0 of JK now. So K is the CM field sitting inside L. The subset here is a CM type. If you apply the complex, so this field has a unique complex conjugation because it's a quadratic extension of the totally real field. And if I apply this complex conjugation to these embeddings, then they should be different from the ones I have chosen. So this should be the empty set. And together, they should make up all embeddings of GK. And starting from this, I define then sigma. These are the embeddings sigma in JL, such that sigma restricted to K is in sigma 0. And similarly, I take sigma bar. This is the embeddings such that sigma K is restricted to K is in sigma 0 bar. This is called the induced CM type. And so you should think of this only as just a way to label things here. These CM types are everywhere in the theory of complex multiplication. They are necessary datum. But if you're not so into number theory, you can ignore this also. So now the fact is the following, and that's really a deep, deep fact. So there exists an abelian variety. A defined over some K number field. Okay, it's a number field. Such that if I look at the complex points, it is given by the following. So you take C to the power sigma, and this is just a short notation for I take as many complex copies of the complex number C's as I have in sigma, and that's isomorphic to C to the D in this case. And you divide here by the integers OL in that field. So these are the integers in L. And you embed the integers here exactly by this embedding sigma. Yeah, so the map here to see sigma, simply a lambda here goes to the array sigma lambda sigma and sigma. And this is an abelian variety with complex multiplication by this ring of integers. So this has somehow an endomorphism ring which contains OL. Yeah, so this is it's an abelian variety with complex multiplication by OL. This means it has many endomorphisms, and in particular, it has an action by gamma, which I set to be the units in, this is acts on A by automorphisms. These are the units. Okay, so we have an abelian variety, so we have a variety over a number field, and this has an additional action by a large automorphism group. So this is a group which contains a free part of rank D-1. Okay. Okay, so this abelian variety, yeah, this is all in the, so this is this quotient. So as a topological variety or C-infinity variety, this is of course just 2D copies of the circle. And you might think, okay, why not applying the results I explained on Tuesday in this case? But it turns out that the cohomology classes would then sit in the degree 2D-1, and that's not good because we cannot do anything with them. We need to have a different approach. Okay, and now what I'm starting to do is to explain you how these Eisenstein-Kronecker classes are built. And I will do this in a little bit more general setting, which is convenient later, because here we consider an abelian variety over number field, but to get integrality results, the integrality will depend somehow on the base here, so on the base field. And if we avoid the places of bad reduction, we can spread out the abelian variety also over the ring of integers of K, maybe inverting some finite places. And that should be also in view. So I consider here more generally a base S, which is the spectrum of R, and R is just some Noetherian ring, commutative as always. And the examples to keep in mind is R is the field K itself, but later, more importantly, I take the ring of integers in K, and then I invert some finite set of primes S. But there are many more possibilities, and how to set that up. Okay, so now we have to go a little bit into the geometry of these varieties. And for this, we have in particular to consider the dual abelian variety. Sorry, spec R. Mahesh. Sigma is also taken. What can I do here? Yeah, some product of primes P. So, not enough letters in mathematics. That's clear. Okay, so we consider now the dual abelian variety, which I denote like this, dual abelian variety. And that's, of course, just the Picard variety of A, pick 0 of A. And this classifies line bundles on A. And this means on A times A dual, I have a universal such line bundle. Yeah. I have universal line bundle. And that's called the Poincaré bundle. And I denote it by P. Yeah, this is the Poincaré bundle. Poincaré bundle. So this Poincaré bundle will play now a major role here. We consider now the completion of that bundle. We make it into a formal scheme by taking the completion along A times the unit section here. So consider P hat, and that is just the formal completion along A times E dual S. So this is the unit section of A dual, unit section. And this is the formal completion here. And because somebody mentioned jet bundles last time to me, this person now disappeared. So this is the kind of jet bundle along somehow this section. So this we considered as a sheaf on A. So let me be a little bit more precise here. So what we do is the following. So we let G denote in OA times A, the structure sheaf here. We let, this is the ideal sheaf of the closed subset A times E dual S. And then we can look at, so P hat, this is just the inverse limit then over K of the following thing. So we take P and tensor this over the structure sheaf. It's a line bundle. So complex vector bundle of dimension 1, if you wish. And we tensor this with O times A dual over J to the K plus 1. Yeah. And you see, this looks already a little bit like this logarithm sheaf, which we had before. And in fact, it will play the role of this logarithm sheaf here. Yeah. So, and to understand that a little bit, how to think about it, let me write down the following. So, the Poincaré bundle is, as one say, rigidified. So if I pull it back along, so more precisely maybe along E times it upper star, this becomes really the structure sheaf. So it's trivialized along the unit section. And this implies that if you pull back this completion considered as a sheaf on A, what you get is the completion of the structure sheaf at 0, completion at the unit section, this you can think of also as being the structure sheaf on the formal group of that dual variety. Yeah, so A hat, this is the formal group of that dual abelian variety, and this will play a role later. So this P hat, this should be considered as a bundle somehow of OA hat dual models over A, yeah, and in the same way as the logarithm sheaf was somehow a sheaf of modules under this completed group ring. Yeah, it really plays exactly that role. And now we have the theorem completely similar to what we had there in the topological case. So if I compute the cohomology of that, here I have to make everything canonical, I have to go tensor here with the these exterior powers, so the D differential forms on A over S. And then I can compute this, and this is 0 if I is not equal to D, and it is canonically isomorphic to R. Yeah, this is the global sections S over I non-D, and if I is D, then it is this R we started with. Yeah. So this theorem is not completely trivial to obtain. You need some deeper inputs. So the first thing, or maybe not ideal, but you need first of all the known cohomology of the Poincaré bundle. Yeah, and this is known, and it has essentially the same vanishing property as this. So there exists only classes in degree D and nothing else. And you need also the theorem of formal functions, cohomology of formal completions of sheaves by Grothendieck. Yeah, so the theorem of formal functions by Grothendieck. Okay. So now we have still this action gamma, and this we haven't considered yet, but because everything here is canonically attached to everything, if we have automorphisms on A, we have automorphisms on the Poincaré bundle, and so on. So on everything acts the group gamma. So so we note that gamma OL star, this acts on everything. And this means we can consider also gamma equivariant cohomology of that. So we get the following corollary, which says if I take the gamma equivariant cohomology, if I take this, then I get the following. So I get 0 in degree I less than D, and I get again R for I equals D. But there might be non-zero higher dimensional cohomology groups. So at least in the very general situation. Sure. Yeah. Yeah, I mean that's a good and interesting question. Of course, you can somehow, you see, if I consider real torus and dual real torus, yeah, then I can have something like the Poincaré bundle on this. But the problem is that somehow, if you would like to do something with coefficients in arbitrary commutative ring, then this doesn't help so much, because the bundle there, this is somehow, it's as here, yeah, it classifies, it is somehow the universal line bundle on this, yeah, and so at each point this is attached to a character of your torus, and but this has values in S1. And so the analogy is not quite perfect here in this sense. But I will tell you later, it has a good reason. This is not the good thing really to consider in general, but it is the thing where we land in and which works. And I explain to you later what is the right analog of the logarithm sheaf we had earlier. You will see this. Yeah. So we have that equivariant cohomology. So let me make the remark if you haven't seen this before. So the equivariant cohomology, gamma equivariant cohomology, you get by taking the derivative, so derive the functor f goes to, you take the global sections of your sheaf f, and then if it is gamma equivariant, that's of course needed to make gamma equivariant cohomology, you take the gamma invariance of that. Yeah, this is then a gamma module, and you take the gamma invariance. And so it's a composition of two functors, which means you have a spectral sequence. Converging to this, which looks as follows. So you have the group cohomology of gamma applied to the jth cohomology of your sheaf f, and this converges to the I plus j cohomology, the equivariant cohomology with respect to gamma. Yeah, and with this, it is and the results we had, it is quite easy to compute these groups, and you get this result. Okay. Now, how to construct the classes? Sure, please. A what version? Yeah, in a certain sense, this is what you need. So you see so if your group is nice enough, then you can, of course, always compute the group cohomology by looking at the topological singular cohomology of the classifying space of the group. And the classifying space, B gamma, in the case of the units, you have to be a little bit careful here. This would be something like L tensor. We have to be careful. So let me write it as follows: R to the power D bigger than 0, positive integers, and then you have an action of the OL D star here. So at least write it as sigma, then it's maybe clearer. So if this would have no torsion, then this is the classifying space, and you can simply express this in terms of differential forms on this manifold. Yeah, this we use in computing explicitly the classes. So now, very similar to the topological case, we now need to fix some torsion subgroup of the abelian variety. And for this, we say D is just the kernel of an isogeny C from A to some other abelian variety. I don't care what it is. The only thing I care about is that this C, this is an étale isogeny. Étale isogeny. And that the dual isogeny is also étale. So I'm writing this on purpose a little bit more difficult. Last time I simply said, okay, so for example, maybe that's all I want to say. if you take the n multiplication, if n is invertible in your structure sheaf, yeah, then this is true, for example. So this is an abelian group, so you have something like n multiplication. It is also an étale morphism, yeah. Okay, so we have the following situation. We have this is then finite étale, and this sits in A, and we have also the complement here, which we call UD. Yeah, this is the complement of this, and this sits over our S pi, and we have such a diagram. And now we're exactly in the same situation as we have been on Tuesday, and here we can now look at the long exact cohomology sequence. The localization sequence in this situation. And this would start again with hn minus 1, and we do it directly equivariantly here. So A gamma of this p hat tensor omega d, so I don't write now the A over S here all the time. Then you go to hn minus 1 ud gamma equivariant cohomology of that. And then you go on, you have to go to this cohomology with support in D. And it's no longer, we look at D. So the N from Tuesday is now the D. Yeah, sorry? A prime is any other abelian variety. Yeah, any abelian variety. You see, I just, in the applications, I just don't want just to look at n torsion points. If this has complex multiplication, I can take any ideal in my ring OL, and I get a multiplication map here. Yeah, so, and I want to consider this as well. If you're a little bit worried with this, then stick to this, that's fine as well. D, that's just the kernel of that map. So, yeah, D is the kernel of that map, of such a map. Yeah. For example, yeah, in this example, D is the n torsion of the abelian variety. Yeah. Good. So you get this sequence, and by the theorem we had, or the corollary, this is 0. So we get somehow that the classes in here are uniquely determined again by what they do in their support in these torsion points. Yeah. And the sequence goes on, of course. I should put in here one further thing, and that is the D cohomology of that. So D A gamma omega d, and that turned out to be R. Yeah, so this is what we have. So in the topological case, one could somehow do with excision and so on. One could prove this isomorphism. One could identify this group. This is no longer the case really for abelian varieties, because now we're dealing with coherent sheaves. And so we have to prove some difficult thing. And the theorem says, if I take the global sections of this D, so for example, n torsion points, the structure sheaf, and take the gamma invariance, then this injects into this cohomology with support. Yeah, and that uses really difficult purity results for coherent sheaf. So this means we have now, yes, not I have unfortunately not enough space to make this a nice diagram here, but we can now produce cohomology classes by starting with just some functions supported on the torsion points. Yeah, that's like the alpha we had on Tuesday, and this will be exactly the same, only it will not be called alpha today, to derange you a little bit, but also I try to keep some of the notations of the paper I'm talking about so that it's easier for you to compare this with your notes. So, so the corollary is the following, and that I get a map, so which we call the Eisenstein-Kronecker map associated to gamma and A, and this goes from this global functions on the torsion points. Yeah, they're not, so if you think of this as just a bunch of n torsion points, this is just, you give somehow for each point just a value in your ground ring R. So that's nothing very hard to write down. Yeah? But we have to be a little bit careful. We have to, so I want to abbreviate. That's not good. Sorry, I have to write this something in before to have a short notation. So I write OD 0 gamma to be the kernel of the global sections on D, OD gamma invariant to R, which comes somehow, you see, we have the injection of this group into here, and then we have the map to R. So every element we have here, a function on the D torsion, which maps to here and then goes to 0 there, this will give a unique cohomology class. Yeah, so I need something in this kernel, and I write this kernel like this. Yeah. If you find this suggestive or not, I cannot say. But we use this notation. And from there, we have now a map, yeah, to this group. Yeah, so we produce somehow cohomology classes there and unique cohomology classes. And this we call the Eisenstein-Kronecker. Classes. I have many. Okay. Okay, so one can here work in more greater generality. Let me point that out, because this is really a not story somehow only begins here. So works in greater generality. So that's some projects for the younger persons in this room. So all the ones which are younger than I am. Works in greater generality. So for example, you can use abelian schemes really over some general basis. You can also do the equivariance more interesting. Yeah, so use GLNZ, which acts naturally on A times A and factors. Yeah, so you can do something like this, then you get group cohomology classes in GLNZ. And if A has Cm by K, yeah, so A Cm by K, A Cm by OK, then you get, you can take also A times the product of these varieties, n factors, and you get then that you have an action of GLN OK. Yeah. So many interesting cases are possible, and the moment I have an ongoing thesis who student Chenghang Du who investigates somehow the case of GL2 over an imaginary quadratic field, and this should also give interesting algebraic Eisenstein series, but there are really many things to do. Sorry? Which general, more general? This here? I mean, you get, you will see if I write down my theorem. So you get cohomology classes here, and the cohomology classes we can compute explicitly in terms of certain Eisenstein-Kronecker and Eisenstein series. And here, to write them as Eisenstein series, you get algebraicity results for these Eisenstein series in higher dimension, which are not always known, especially for GLN-Z or GLN-OK. That's not, it's open, yeah? Very difficult things. So there's something to be done. Okay. So unfortunately, this is the first remark. That's a nice remark. But the second remark makes, unfortunately, things more complicated. So if you investigate that case here, you don't get all Eisenstein series you need. And so this will give only so-called, so to say, holomorphic Eisenstein series. Eisenstein series, and we need also derivatives. Yeah, if you remember my first lecture, then I said the strategy of Shimura was somehow produce algebraic Eisenstein series on the moduli space of abelian varieties with real multiplication. And you prove that the Eisenstein series are algebraic by looking at the Q development, and you use the classical holomorphic Eisenstein series there. And then you have to look also at the effect of the so-called Shimura mass operators, and that they are also algebraic on this Hilbert modular variety, and this gives you then algebraicity also of the derived classes. We need some substitute here, and the interesting thing is that this can be done not working on the moduli space, but working on the abelian variety itself. But for this, I have to explain to you how we do this. And unfortunately, we need to generalize this a little bit. So the problem turns out to be problem P has no natural connection on it, which we could use to derive classes. And we remedy this fact by going over to the so-called universal vector extension. The idea is use so-called universal vector extension of a dual. Yeah. And this is the following. So this is a group scheme, a sharp, which sits over the dual abelian variety and in an exact sequence. So this is the surjective map of group schemes. And the kernel is a vector group scheme. And the vector group scheme is omega A over S. So this is just E upper star. So it should be maybe, yeah, it's E upper star of omega 1 A over S on the base. So that's somehow the dual of the Lie algebra, if you like, of A over S. This is just a vector bundle. Yeah, and this vector bundle I consider as a group scheme, and that's the sequence. And so this is an extension by the vector group. The vector group. Namely this omega AS. And that's the reason for the name. It has a certain universal property I don't want to go into. The important point here is, so the fact is that this A sharp, this classifies not only line bundles, it classifies line bundles together with an integrable connection. It classifies line bundles plus integrable connection, maybe L integrable connection, nabla from L to L tensor omega 1A over S, which has the property that the curvature is 0. Okay, but that means, so these are this classifies pairs. So if we go to A times A sharp, we will have a universal bundle with a universal connection. Yeah, so this gives on A times A sharp have the universal line bundle P sharp with connection nabla, and because the line bundle P was already universal, as a line bundle, this P sharp has to be just the pullback of the line bundle P. Yeah. So and P sharp as a line bundle, this is just the pullback of the identity times this map P here from the Poincaré bundle downstairs. Okay, and so we have now a connection, and we want to use this to derive our classes. And this we can do because we have coherent cohomology classes, and we will do so. But first, we have to consider the following. So now with this line bundle on this, we can somehow play the same game as we did for P. So we can consider the formal completion. Yeah. So so this is we can consider formal completion of this. P sharp along now somehow A times the unit section of this universal vector extension. Yeah. Unit section. And we consider this again as a sheaf considered as a sheaf on A. So now, in fact, I can comment a little bit more on what Mahesh has asked. This sheaf, together with its connection, this is somehow the Ram realization of the motivic logarithm sheaf. That's the right sheaf to consider. Yeah, so it is, so the analog of a local system in the Ram cohomology is a bundle with an integrable connection. Yeah? And that's exactly this, together with the, so on this formal completion, you still have this connection. Yeah, that's, and one can prove that this is really the logarithm sheaf in this theory. And so that's something what is the right analog. Yeah, this is due to the fact that somehow if you consider all C star valued characters on your abelian variety A, the parameter space for this is really the universal vector extension. Yeah, you see the universal vector extension is, as an analytic manifold, it is isomorphic to something like C tensor lattice divided by lattice. So it's just a copy of C star, D copies of C star. So that's 2D copies of C star. Well, what I'm saying? Let's see. That's D copies of C star. Okay. So that's the right analog. But it turns out that our classes really live already here. And if you would have done the same construction with this sheaf, then you have to stay in the category of modules with connection. And then you get somehow an analog of the topological class, which has cohomological degree 2D minus 1. But we need something in degree D minus 1, which I will point out later. Yeah, so it's really important that we work with this Poincare. Okay, so then one checks that somehow this P hat just sits inside, yeah, this P sharp. So we can somehow, the cohomology classes we had, we can extend them simply to the sheaf, and then we can take the derivative, and we get somehow a derivative operator. And we take the eighth iterate, so this is the eighth iterate of the connection. And this gives us the map D minus 1 UD gamma P hat. We embed this into here, and then we apply nabla several times. And when we do this 8 times, then we land up no longer in omega 1 of A over S, but in the tensor symmetric power of it. So we go into HD minus 1, UD gamma, and then we will have the 8th tensor symmetric power of omega 1 A over S, tensor P hat sharp. Yeah, because we had to extend coefficients to this. And then we have also the omega D as before. Okay, so we can somehow derive our classes now. And so we get from the Eisenstein-Kronecker class here, gamma A, rho, we get at nabla A, EK, gamma A, rho for all rho in this OD, these functions supported just on the torsion points. Yeah. So the point here is really we have now differential operators used on the abelian variety and not on the base. Yeah, so we can avoid all these problems that there is no moduli scheme for the Eisenstein series we want to talk about, but we will still get them. So now we consider the evaluation at torsion points of these classes, and they can then be computed. I mean, these classes can also be computed, but it's much more difficult to write them down. And I want first to explain to you. Now, so far, complex multiplication didn't come in. Yeah, I mean, maybe I should point that out. Complex multiplication so far was not used at all. Yeah, so it's only we have an abelian scheme with a gamma action. That's all. Okay. So, evaluation. Torsion points. So how does that go? So we fix x in UD. This should be an F torsion point. Yeah, so F and this F and C, they should be somehow co-prime, whatever that means for isogenies, but later they will be given really by ideals in OL. And we want to consider the pullback of this class, which we just constructed. And we pull back to the base. So we see this X as a map. Maybe you write it more explicitly from the base to UD. We want to pull back that class, and then we want to understand it. And there we want to use somehow also the complex multiplication. So, and to see where we land, we have now to go through several steps. That's unfortunately a little bit technical, but it's important to decompose all this to get at the right part where the Hecke character, where we get the right infinity type of the Hecke character. So, so first we have the following. So we have a map x upper star from the asymmetric power omega 1 a over s tensor this completed Poincaré bundle omega d 2. I mean, these are all equivariant sheaves, so we get simply the small omega omega a over s here. And here we have a map to this formal completion of the dual abelian variety, to the ring structure ring here. And here we have omega a over s to the power d. Yeah, so that is the first map we want to consider. And now I have to recall some facts about abelian varieties with complex multiplication and their Hodge decomposition. So facts. So the first fact is the Lie algebra of the universal vector extension over S. This is nothing but the relative first de Rham cohomology of A over S. Yeah, that is somehow lies in the crystalline nature of this universal vector extension. And we define H to be the dual of H de Rham A over S. So this is the dual. So this is the OS dual. This is some vector bundle on S, and we take the dual vector bundle. So, and taking the Lie algebras of the extension defined, so the universal vector extension, this is a sequence of group schemes. So we can take the Lie algebras and we get an exact sequence here. And what we get gives the following sequence, omega AS. And then you go to H1 de Rham AS. And then you go to the Lie algebra of A dual over S. And this is something you might have seen before. This is exactly the Hodge filtration on the first de Rham cohomology. Yeah, so this is encoded in the universal vector extension. Okay, so this is this is the Hodge filtration on H1 de Rham, the algebraic Hodge filtration. And now the point is that, and that's really important for the algebraicity, in general, this Hodge filtration, this is not split. Yeah, for an arbitrary abelian variety, you cannot naturally split it. But for CM abelian varieties, this is possible. So fact, if a CM abelian variety, then we have following decomposition. So the Rham cohomology splits into omega AS direct sum Lie A dual S. Yeah, and this is like the H 01 plus H10 decomposition of the H1 de Rham. This is some of the Hodge decomposition, and in this case, yeah, this is in general even. I mean, this is never an algebraic splitting, which you get. This depends on analysis on the theory of harmonic forms, but here it is possible to have an algebraic splitting. So this is the algebraicity of the Hodge decomposition. And okay, we have that fact, but we need unfortunately more. Namely, we have to look now at this completed sheaf, and we have to understand there's some mistake here. So we take this, there should be not a dual, but some of the formal completion of the vector group. Sorry. Yeah, please. That was not correct. So for the completed group ring, we had something which I called the moment map, and the fact is that we have this for this sheaf as well. We can really write this. This is the formal completion. So this is a group ring of a formal group, and you can non-canonically write this as a power series ring. But if you want to have something canonical, which also reflects somehow the group action of gamma and everything, you need another map. And this exists. There is a canonical map. From OA formal completion, which I call again the moment map. to the product over all B bigger or equal to 0 of the B symmetric power of that sheaf H, which is just the dual of this H1 Dirac. Yeah. And with the algebraicity of the Hodge decomposition, we can split this further. So we have a map, B bigger or equal to 0, T sim B of omega A dual over S, yeah, by algebra. This is projection, which exists only by this Hodge decomposition, yeah, by the algebraic Hodge decomposition. Okay, and so why does that exist? So in general, you don't have that, but here, this is a formal group, so this uses A. Formal completion of any group scheme is just a formal group, completion at the unit section. That's a formal group, and this implies that one has a map. So this is a Hopf algebra then. So you have a map from OA hat sharp to OA hat sharp tensor OA hat sharp. Yeah, Hopf algebra map. And if you iterate that and go then to the first infinitesimal neighborhood, in this first infinitesimal neighborhood, you see the sheaf H, and if you take then B symmetric powers, you get that map. Yeah, that's a little bit technical, but that is the essential input. Okay. So that. Hopf algebra, this is an algebra which has a multiplication and a co-multiplication. So if you have some group scheme, affine group scheme, yeah, then you have, so if G spec A is some affine group scheme, then A is, of course, a ring which defines this group, but then we have a map, the multiplication map, from G times G to G, and because this is an affine scheme, this gives you, this is equivalent to give a map from A to A tensor A. Yeah? And that's a co-multiplication, and because this is a group, so this satisfies associativity law and so on, and in this case, in our case, even affine. So that's okay. Good. Yeah, unfortunately, that's not all what we have to do. We have to decompose that, unfortunately, even further. And for this, we now assume that R, the ground ring we're working with, is OL 1 over DL. Oh, sorry, that's L Galois closure algebra, yeah, where L Gal is the Galois closure of L. And DL is just the discriminant. If this is the case, you can decompose into embeddings. So what you get is then this omega A over S. So as a gamma OL star module decomposes into just the sum sigma in sigma. This is this CM type, which was there somehow from the beginning if we have a CM abelian variety, omega AS sigma. And that's the part where gamma acts via sigma. Yeah, this embedding on this. Yeah, so this is a sigma eigenspace. Yeah. Okay, so we can do that, and similarly for omega A dual S, and you get here that in fact only the sigma in the complex conjugates are involved. So you have here omega A dual S sigma, say sigma bars here. Yeah. Okay, we have these decompositions, and with these decompositions, we can now decompose the symmetric algebra further. And now you see if the module you have decomposes into the direct sum, the tensor symmetric algebra, this is the tensor product of the respective symmetric algebras. So this here, this decomposes into the sum over all alpha. These are just sigma tuples of natural integers, which sum up to A. And then you have, then I write T sim alpha of omega A S, and by this, this I mean, so this here is defined. This is defined to be the tensor product over all sigma in sigma, and then you take T sigma alpha sigma. This is now an integer of omega A S sigma. Yeah, this is some sheaf. I take it to the alpha sigma power, take the tensor product over all sigma and sigma, and this I denote by this. Yeah, and that's now a complete decomposition here. Okay. And of course, similarly, we have that for the Beeth's tensor symmetric power. So that's unfortunate to do this, but that's quite important that we get the right classes. So, and T sim V S, this decomposes also as a direct sum, and now beta in n sigma bar, and they sum up to B. And with the same convention, I write here T sim beta dual over S. Yeah. So putting all that together, we finally get the following classes. Yeah, we can we can take x upper star from our derived classes, ek gamma a, for some function rho. And now we take the moment map to it. And now we can decompose this into types alpha beta. Yeah, so alpha beta type. And this is then a class in HD minus 1 of the base, equivariant with respect to gamma. And it sits here in T sim alpha omega as tensor T sim beta omega a dual over s tensor omega d as. And in fact, I can identify this, and maybe I will do this. So this here is, of course, this is just the tensor product of the omega a as sigma. Sigma runs over sigma. And I can put this into here by writing so T sim alpha plus 1 sigma omega as. This is just putting these two together. It's not equal. That's inside. This contains T sim alpha omega as to this omega d as to get rid of this factor. Okay, so we have that class, and this is the class we're interested in. But before we go on, we now realize that because S is affine, the spectral sequence collapses completely because there's no higher cohomology on an affine scheme with values in here. So this gives you just the group cohomology in degree d-1 of the global sections of this. So, and I now write alpha plus, with this convention above, omega as tensor T sim beta omega a dual s. So now we have to reflect for a second. Maybe I give the class a name. So this in here, I call it ek gamma a rho x, and then here I put beta alpha. Now it's a good point to reflect for a second what we have here. So with all that effort, we have produced now the following. We have just the group cohomology class for the group gamma. And gamma, this is in our case OL star. And this is an abelian group, or a subgroup of this we can take. So this is an abelian group which has rank exactly d-1. So we're sitting in the top cohomology of that group. And that means we can evaluate it. And this we will do. And so I should put this remark maybe here. So the rank OL star, this is d-1. Because then we can use the cap product with a class in the homology of this group, values in R, to get something which is just an algebraic section of this bundle. Beta. So we have produced an algebraic section here, and so that without any other knowledge about that class, it is an algebraic section. What it is, we have to compute, and we can now again make this trick we did somehow in the Tuesday lecture. I mean, we are now over a base S, say a number field K. But to compute, we can extend coefficients to the complex numbers and compute however we like. Yeah, and that we will do. And that's the most technical part of the whole story. That was only a light technical part. But the point is, these classes are algebraic group cohomology classes. And if you think about the examples which I gave, where one could consider this as well, it is extremely interesting that to consider groups like GLN-Z here. Yeah, so for GLN-Z, the locally symmetric space is not algebraic. So this means there is no way somehow to construct algebraic cohomology classes by considering somehow the Shimura variety associated to this and then work there. That would be the classical approach, because there is no Shimura variety attached to GLN-Z, yeah, for n bigger than 2. So, but we construct nevertheless, even in such a case, we would produce algebraic cohomology classes. Yeah, group cohomology classes, and that's something very hard to do. Okay, and it was hard enough, yeah, as you've seen. But now, and I spare you the details, we compute that, and that's really possible with a Fourier series approach, which also worked in the case of real tori, so in the topological setting. And we have the following explicit formula now. Maybe I have to say one further thing. So we have now these algebraic cohomology classes, and if we want to have a function, really a value, we have to choose basis here. Yeah, so choosing basis say omega A sigma of omega A sigma. This is a bundle, this is a section, and also of omega dual S sigma bar. Yeah, one can trivialize this bundle, and one has a map from this T-sim alpha plus 1 sigma omega AS, T-sim beta omega A dual S to R. Yeah, by evaluating at their spaces, please. No. I mean, this was a general remark, but there's also, I mean, if you look at this unit group, yeah, there's also somehow the locally symmetric space associated to that group would be something like R to the sigma greater or equal to 0 divided by OL star. Yeah, and that's also, this is never an algebraic variety. Yeah, this has no complex structure. Yeah, and this is, I just wanted to point out, if we do the same thing and use a bigger group acting, then we would get cohomology classes here, which are algebraic, but somehow the underlying group, the underlying arithmetic group, has no good moduli space attached to it. Yeah. In this sense, exactly, in the sense how one could generalize it. In fact, if you look closely, the classes we have, I mean, because the presentation is already difficult enough, I don't choose not to make that. But the point is, they are in fact, so in fact, these classes live in the group cohomology class for the group GL degree L over K, okay. Yeah. So they are really classes for that group. Yeah. K is the CM field in here. So if this has degree N, then we are in GLN OK. And for this group, there's also no moduli space. That's exactly the problem. That's good that you asked. I mentioned in the beginning. So this is the group where the Eisenstein series we want to construct live somehow in this locally symmetric space. Yeah, for this arithmetic subgroup, there are the Eisenstein series we want to have. But this arithmetic subgroup, this has not attached to it an algebraic variety. We are lost. Yeah, so that's too bad. And Shimura and so on, they were in a case where there was an algebraic variety. But our construction doesn't use any moduli space. It uses equivariance. Yeah? And this somehow, this is a trick you should maybe keep in mind if you keep in mind anything of this lecture, that if you have an arithmetic group somewhere and you want to have algebraicity results, then it's maybe very interesting to look at equivariant. In the equivariant situation, equivariant cohomology. Yeah? Okay, so this gives really equivariant, it gives in the end an algebraic section here in R. And if R was some integer ring, it gives you integrality and everything. Yeah? So, okay, now let me write down explicitly what we get. So for this, let now lambda in C to the D be the period lattice. Of the map attached to this basis omega A sigma. Yeah, this gives you a map from the Lie algebra A over C to, or an isomorphism even, to C to the D. Yeah, so that's now, this is a basis of algebraic differential forms. And now I have the lattice H1, the first homology of AC with integral coefficients sitting in here. And the image of this will be then the period lattice. And so we take that and we take some C torsion section in the period lattice, so an element in here. That's a C torsion. Then we define the Eisenstein series. Follows. Beta alpha Ts lambda gamma. And this is the sum over lambda plus T times T. T times, this is gamma times T. Gamma times T divided by gamma, and you have any lambda in here, and then you sum over lambda to the power beta divided by lambda to the power alpha norm S, and lambda to the power alpha is just defined to be the product of sigma lambda to the power alpha sigma, where sigma runs through these sigmas, and similarly for beta. And I should remark here that these Eisenstein series are now related to the L values we want to consider, at least to the partial L values. So the partial L values related to an ideal B of this Hecke character, they are just, you take chi of B times E beta alpha 1, 0, F times B inverse, and here you take the F units, totally positive. I know they're all F units. I have no totally positive here. If the infinity type, which I didn't define, of chi is beta minus alpha, then you have that relation, and summing over the ray classes here, you get the L function. So these are the values you are interested in. And the main result is now that if we take that cup product, so maybe I write it as follows. So I take theorem, I take these classes, gamma A rho X beta alpha. I take the cup product with some generator here, generator in the D-1 homology of gamma R, and then I evaluate at these bases omega A and omega A dual. This is a number, and the number I get, this is just the following. This is some sign. D is the dimension times D-1 half times alpha factorial. This is a multi-index. And then you take the sum over all these torsion sections, C inverse lambda divided by lambda, and rho of minus T times this Eisenstein series beta alpha plus 1 sigma T plus X 0 lambda gamma. And here you have to divide by omega alpha plus 1 sigma times omega beta, omega dual beta. And that's the last thing I want to explain. These are the periods resulting from this period lattice here. So resulting from this basis. So maybe I don't erase everything, only this. The eta is the generator. This is not generator of this homology class. This is an orientation of somehow of the group. Yeah, so that I can, this was a D-1 cohomology class of gamma, a cap with this to get really something in this T-sim alpha T-sim beta, and I evaluate on a basis, and then I get something in R. Yeah. Sorry, this was a little bit fast now. So where omega alpha is the product over omega sigma alpha sigma, and I have to say what omega sigma is. Omega sigma, this is just the period pairing applied to 1 in this basis. So 1 is so the element 1 in OL. So this is the period pairing of omega AS times the first homology of your abelian variety with Z coefficients. So this is just the lattice which defines it originally, OL. And so here I have the element 1, and here I have this chosen section, and I evaluate this, and then I get this period. And similarly, so this is the period, and similar in the dual case, similar for omega dual sigma using the dual basis. Basis of the dual abelian variety. That's all I wanted to say, and thank you very much. overwhelmed audience. Sure. There could be torsion. You have to be a little bit careful with the torsion. So in fact, here in the end, I was not changing the notation. You have to take gamma has now to fix this x torsion point, and this is an f torsion point. So this, in fact, now here in this formula, gamma should be the OF star units as here. Yeah. And we make the F so big that there's no torsion. Otherwise, we can also do something, but that's a little bit more technical. The evaluation map, yeah. And maybe, sorry, please. Alpha can be equal to beta, yeah, but you have to be careful. The condition is that this is critical, so alpha has to be always bigger than 1 in the obvious sense. So all alpha sigma have to be bigger than 1. Yeah, and then beta can be anything greater or equal to 0. That is the condition that the infinity type is critical. Yeah, like for CM elliptic curves. Yeah, we include in a certain sense very well the Birch-Dyer point. Yeah, but we do not get anything for non-critical L values. It's funny that somehow this construction, if you make that decomposition into alpha beta types, first all alpha betas can occur, but then you have this condition that this has to be equivariant somehow for this gamma action, and that kills all the infinity types which are not critical. Yeah. This is strange, but that's so the construction only gives critical L values. More questions?
If there are no other questions, let's thank the speaker again.
Thank you.
You can have more interaction there. We have a small.
Oh.
In fact, we are happy that Professor Mahesh Hecke is visiting us, and we have a small minute for him.
You have to give the talk tomorrow.